Hello, everyone, and welcome to our next session of the Frameless Symposium. This one is entitled The Interaction, Perception, and Technology. And we have three presentations lined up for you today. And I want to point out that there are American Sign Language interpreters, Nikki Cherry and Amanda Dole, here with us to sign the spoken presentations. And they will be voicing a signed presentation for you. And also there are live captions available if you click the CC button at the bottom of the Zoom window. So the first presentation today will be presented by Emily Isenstein, who is an MD and PhD student at the University of Rochester. She's in her first year of graduate work in the Brain and Cognitive Sciences department, and she is interested in haptic perception in individuals with autistic spectrum disorder and plans to study this topic using a combination of EEG and virtual reality. So Emily, please share your screen and present.
All right, thank you, Dr. Murdoch, for the introduction. And thank you to everyone for tuning in. Today I'm going to be talking about the use of virtual reality to assess visual-proprioceptive integration in children with autism spectrum disorder. So I'll start off with a little bit of background on autism. So it is a heterogeneous neurocognitive disorder with several different symptom domains, including social communication, restricted and repetitive behaviors, so things like special interests, and as well as sensory differences. And because it's such a heterogeneous disorder, there is a really wide range of the expressive and as well as receptive language level in this group. And it's a common misconception that intellectual disability is a key component of autism, but it is not one of the core symptoms there. But because it is a comorbidity in a lot of people who have autism, there is a really wide range of the level of support needed by these individuals. And before I really get into things, I did receive a number of questions about the feasibility of using virtual reality with individuals with autism. And so far, we have been very successful. We've run the experiment with 11 children so far with really no issues. It runs about the same whether the child has typical development or has autism. And in general, virtual reality is getting to be more and more common in research with this population, particularly with things like social scenarios, having the participant interact with some kind of avatar. And in 2020, there were over 30 different publications on PubMed that used virtual reality with this population. That being said, there are some specific considerations that you should make if you want to use this technology with this population. And like I mentioned before, a good proportion of people with autism do have a comorbid intellectual disability. So if your experiment is going to have some kind of active component, then that is something that you need to be aware of, that you may need to screen for cognitive processing before enrolling people in your study to make sure that they can follow the instructions and participate. There are also some sensory demands with VR that may affect individuals on the autism spectrum differently. So many autistic individuals are hypersensitive or hyposensitive to different sensory stimuli. That's just something to be aware of when you're designing your experiment. And along the same lines, cyber sickness can be an issue for anyone, but individuals with autism may be more susceptible to it. But just in general, if you want to run research with this population, you just need to plan ahead and kind of use visual supports to provide an idea of what the person is going to be doing, so they know what to expect and there are really no surprises along the way. And just in general, it's good to be flexible about your research plan. So I'll also talk a little bit about sensory perception in autism spectrum disorder. And there has been a lot more research about this in the last few years with a focus on diminished multisensory integration in autism. And when I say multisensory integration, that means kind of when you're detecting something that has stimuli from multiple sensory domains. So let's say that there's a fire truck coming around the corner and you can see the flashing lights and hear the siren. and your brain is able to kind of pair those two together as coming from the same source. So that would be multisensory integration. But in this population, there has been some research done on how these multisensory differences may correlate with symptom severity. So it's an interesting realm of study. With that being said, there really has been very limited amount of research on proprioception and its integration with other senses. Now, what is proprioception? It's not the most common word that people use, but essentially it is your body awareness, and it represents your awareness of self in 3D space. And it's comprised of both knowledge about your position in space as well as your active movement. And proprioception plays a really critical role in early motor planning and coordination. So if you imagine a small child learning how to walk, being aware of where you are compared to everything else in your environment is really important to judge how to take a step and where you are. And it's a very important process in development. And there has been some research on how alterations in this proprioception may contribute to specific features of autism spectrum disorder. So to dig into that a little bit more, differences in proprioception may explain certain symptoms of autism spectrum disorder. So symptoms like these repetitive self-stimulatory movements, reduced gesturing, and difficulty with imitation can all potentially be traced back to proprioception. There's also the possibility of this atypical weighting of visual and proprioceptive information. So when I talk about the weighting of information, I mean, so let's go back to the fire truck example. So let's say you see the lights before you can hear the sirens. So they're kind of offset from each other a little bit. Which information do you use in order to determine where the fire truck actually is? So which information do you weight more strongly when they don't agree with each other completely? And this weighting may be dysregulated in autism, specifically in these visual and proprioceptive domains. And finally, there is some, although limited, research out there on how this difficulty integrating vision and proprioception may correlate with different trait severity in autism. So the goals of this research study that we did was to investigate the weighting of proprioceptive and visual information in children with autism compared to typically developing controls. So when presented with vision and a visual stimulus and a proprioceptive stimulus that don't match, which information do you rely more on? And then ultimately, although we have not gotten to this part yet, we do plan to computationally model the integration of this visual and proprioceptive information in order to better understand motor planning in this population. So now, why are we using virtual reality for this kind of experiment? So on the visual side of things, VR allows us to manipulate and distort what the participant sees. And that's a really valuable thing that has been difficult up until this point. But also with virtual reality, the participant is able to still self-generate their own movement. So they can reach out for something without having something pulling their hand. And it's a very active self-generated movement. So with these two qualities together, we're able to create a discrepancy between what a person feels proprioceptively with their hand movement and what a person sees visually presented in the VR headset. So with this experiment, we're targeting children between the ages of 9 and 17. So far, we have recruited 11 with autism and 6 with typical development, although we are still in the recruiting stage. And we're also collecting some assessments of things like cognitive ability and sensory processing, so we can compare those results later. So now here, this is what the experiment looks like from the observer perspective. So the participant wears the headset, and in their hand, they hold one of the controllers. This is using an Oculus Rift, by the way. So they're holding the controller, and they slide it forward along this track here that can be set to different angles at the table. So now on the next slide, I'll show you what it looks like from inside the headset. So here we have kind of this field of dots that move in tandem with your hand movement. So you're controlling the pace of these dots that move once your hand starts to move. And then these arrows that you see here are the response to each trial. So the participant is asked to judge the direction that these dots are moving in and adjust these arrows to the direction that they believe the dots were moving. So here we have kind of a top-down view of the experiment. So this line here represents the hand motion, so your hand moving the controller along that track. And this line here represents what the participant is seeing. So the really critical part of this task is this angle of offset. So we're able to make what the participant is seeing be different from what they're feeling. So some of the trials, the dots are moving exactly the same direction as the hand, but in most of the trials, they are offset in some way, although the participant does not know the amount of the offset. So for the response portion of the trial, there are two options to what the participant can be doing. So if their response is over here, we call this repulsion. So essentially, this line here is the true direction of the visual dots, but this is what the participant has perceived them to be and their response as to what they are. And we call it repulsion because it has been pushed away from their proprioceptive hand movement over here. The alternative is that they have some attraction here. So again, this is where the dots were actually moving, and this is where they perceive them to be. And we call this attraction because their perception was attracted towards the direction of their hand movement over here. And we had several different configurations for the experiment. So we had two different hand angles here at -45 and +45 degrees. Those were fairly limited just because the time it took for the experimenter to shift the rail around. So we kept those fairly limited, but we did have 3 offsets in either direction for both of these settings that we're able to look at. And so this here is our preliminary data. So this is all collapsed across all of the offset angles so they can all be compared together. And I do want to say again, this is very preliminary. We're only about 1/3 of the way through recruitment, and that's why our standard error bars here are so large. We do have about twice as many autistic participants so far, and that's why the standard error bar is about half the size of the typically developing one. So over here on our y-axis, we have the perceived repulsion. So when we first started the experiment, we were actually expecting to see attraction, but we have seen a very consistent trend of repulsion instead, and we're still trying to tease out why that could be. But the main takeaway from this chart is that even though this is quite preliminary, we are able to start to see this differentiation between the amount of repulsion that the typically developing group has and that the autistic group has. So our current interpretations of this study are that virtual reality can indeed be successful to manipulate vision to isolate and study proprioception. So we are able to use it to affect what the person sees while they're still able to move their hands freely. And although our results are fairly preliminary, the typically developing and autistic groups may utilize visual and proprioceptive information differently when making a judgment that uses both modalities. And although we will wait until we have more data to make any conclusions, it may be that individuals with autism rely more heavily on proprioceptive cues than individuals with typical development, and less so on visual cues. So our future directions, we do plan to continue collecting data. Right now our sample sizes are fairly small, although they are promising. We are also planning to explore other permutations of this task. For example, this task was created on the Oculus Rift, and since we started, the Oculus Quest was released that had the hand tracking capabilities built into the headset. So the Rift, we had to have the person holding the controller in order to track the hand. But with the Quest, we have a task in development as a follow-up to this study where the hands can move freely and don't need to be holding any kind of controller. We're also planning to investigate the association between all this experimental data and the parent report measures of sensory functioning that we are taking. We also plan to look at the role of IQ with the cognitive testing to see if that is contributing to anything here. And ultimately, it is our plan to apply these results to better understand proprioceptive differences in autism spectrum disorder. So the funding for this project is from the Child Neurology Foundation Neurodevelopmental Disabilities Summer Research Scholarship. And I wanted to thank everyone at the Tadin lab at the University of Rochester for all of their help with this study. All right, so I think I have some time now to answer a few questions. I do see a couple here.
Good, yeah, so I just want to point out that there is this Q&A box again at the bottom of the screen. I see that there are already a couple questions posted, but if any audience members didn't find that yet, that's the place to put your questions for Emily, so go ahead.
Yep, I do see that there was one question about whether or not there is a pivot point on the track. The answer is yes. It's almost like, so it's fixed to the table at one point and can slide along to be set at different angles, if that makes sense. And then can the participant move their hand freely or they have the controller on a track? Sure, so the hand can move freely in that it is self-paced and they can decide how quickly they want to move their hand and when they want to start the next trial, but they are limited in that it has to move in that straight line along the track. And then they reset their hand back towards the center, towards their body before sliding their hand forward again for the next trial. But this is one of the advantages of the new experiment we're designing on the Quest, where there's no limitations of the controller. So we are able to have true free movement of the hand.
Are there other questions from the audience they would like to ask? I would ask maybe, and I don't know much about whether this is feasible, but is this mostly for an assessment technique? And that's what I heard, I think. An assessment of this proprioception mismatch, perhaps. And is there any potential for like training? Is this something you can improve with practice or feedback with a system like this?
So right now we aren't really looking as to whether or not there is a practice effect. It's certainly something that is possible given that you can kind of become more accurate as you use the joystick and work through it a bit more. We don't really have any plans for it to be used to assess any kind of particular skills, but we do think that it's a unique way to kind of determine whether or not someone is using their visual information more or less than their proprioceptive information. Does that answer your question?
Yeah, I think so, thanks. I see another question in the chat, in the Q&A box there, if you see.
Yeah, so the question is about whether we're going to use the Quest 2. We had already started the development of the new task with the original Quest before the Quest 2 was released. And given that they have fairly similar capabilities, it probably won't make too much of a difference whether we use the original Quest or the Quest 2, because we don't really care as much about, resolution and quality per se, because the Quest 1 is really at least sufficient for our needs. But it's the kind of thing that probably could be adapted to the Quest 2, and we're looking into that now. And I think our lab has its first Quest 2 headset arriving shortly.
Okay, well, with that, I thank you for your presentation and for your answers to the questions, and we'll go ahead and move to the second presenters. For this next presentation, we have three presenters who hopefully can come on camera now. Good. We have Dr. Joseph Hill, who is an associate professor in the Department of American Sign Language and Interpreting Education in the National Technical Institute for the Deaf at RIT. Dr. Hill is also a lab director of the Deaf Studies Laboratory, which is housed in the NTID Center on Culture and Language under the directorship of Dr. Peter C. Hauser. Currently, Dr. Hill conducts two research projects, the Language Evaluation Study on Sign Language using Signing Avatar Model and the documentation of individual ASL variation at NTID. The second presenter who will be involved is Andrew Smith, who is a fifth-year BFA student in 3D digital design, and he has years of experience with motion capture technology to make animated characters. He guides the motion capture team on developing 3D animation and motion capture skills. And third, Youmee Lee is a second-year MFA film and animation student who has been coordinating the motion capture lab and directing students on this project. She specializes in 2D and 3D animation. So please continue with your presentation.
All right. Good afternoon, everyone, and thank you for coming to our presentation this afternoon. We'll be talking about the challenge of preserving captured sign language data in human avatar models. So the three of us on the team presenting today, in Rossika Hall, there is the NTID MoCap Studio, the Motion Capture Studio. It's 3D Animation Studio, more specifically. We encourage deaf and hard of hearing students to use this space to improve their skills working on 3D in 3D environments. This has cameras surrounding the room, and the person in the middle has on a black suit with white sensors that the cameras detect. I will show you a sample of what this looks like. One thing I do want to emphasize, the person in the video is not involved in the study. This is just for demonstration purposes only. As you can see, as the person is moving, telling a story, you can see facial expressions that are happening, which are very important to capture. If you do not have the facial expressions in a visual language like American Sign Language or a sign language in general, you will miss a lot of grammatical information that is important to the communication. Before I talk more about what we're doing in our project, with our project on this team, I want to explain a little bit why we're doing this work, some of the background related. Sign language does have variations. There's American Sign Language, ASL, to an English-based sign system. Previously, people thought that American Sign Language, because of its different grammar, did not fit English and there was something wrong with it. So someone created a sign-based system using signs that fit English grammar. So deaf people go into school for their education. They're exposed to a variety of sign modalities and sign languages, which happens to cause variations across the board. So with language attitudes, we study that we can see that it doesn't matter whether it's ASL or English, French, or Japanese Sign Language. People tend to look at the person signing and make judgments based on what they know of the country or the people using it. Similarly to spoken language studies. We would like to be able to manipulate signed language users as you can with spoken language. You can manipulate spoken language to make it sound like a male or a female or someone with an accent. You can not have to see a person, you can listen to them and envision what they might look like. With sign language, it's very difficult to take the person away from the signs and the sign language that is happening. So if you see someone signing and you start to respond, I'm not sure, or you may not be sure if it's because of the way the person looks or whatever may be the case. So in order to be able to separate the person's looks from how they're signing, we can use avatar technology to adjust and manipulate for gender and race. So to be able to work on an avatar and do this work with avatars, we needed to have someone signing, but we wanted to have the same story every time. So we use a prompt video, a cartoon video that is used standardly in linguistic studies. We used this cartoon video. This is an example that I'll show, the first video. And then the second video that I'll show will be with the avatar signing the story. So that was the cartoon video, the story that we used, and then you'll see the avatar signing what happened in the story. Now you can see there are 5 different avatar characters. You can see on the slide, one is the blue person, blue-greenish person, has no race identifiers and no gender identifiers. It is an ambiguous avatar. So we want to focus on signing only. That's a control. Then you can see the other 4, they'll be signing the same, but we changed the looks of them. The next video will show what it looks like with all of them signing the same thing, but looking differently. I'll now turn it over to Andrew. All right, we're talking about motion capture gloves. These are important because the movements of the fingers are necessary to be able to show sign language clearly. So with human rigs, you can see the character rigs and the animation rigs that we use to capture the action. Then the animation rig is put over the character rigs, and we can make it a male or a female and change the size rotation as well. We can connect all of these on the system in the system to make them all 5 characters if we choose to. So we want to show some challenges and solutions. For phonetic phonemes, the eyebrows, the eyes, the cheeks are important, but it is important to show how they work. And we use blend shape. So we have a neutral face. The mouth movement becomes an open mouth movement. We can double copy and paste, then connect it to the neutral face. And then we can control how the mouth opens in that way. I want to mention that we connected the face to the performance avatar. One of the biggest challenges is for the signing motion capture and the facial expressions and the time lapse. So I'll now show a video of how we work with this system. Okay. Now we'll move on to Youmee.
If someone wouldn't mind spotlighting me. Oh, got it. Thank you. All right, hello everyone. So recently Andrew just mentioned all of the facial expressions and all of the movements we had to deal with. And so right here is a picture of the headgear we used to capture all of the facial expressions and movements within the signer's movements. And so a big challenge we had with the headgear, it's industry standard and it was not designed specifically for deaf individuals, and it was not hand friendly for actors and even hearing actors use gestures. It definitely had an interference, and we have a specific example showing you. So I asked the audience to please pay attention to the movement and placement of the sign rabbit. So pay attention closely because we're going to do a comparison later. So you could see that the headgear actually had an interference with the avatar signing. And so here's another example without the headgear with the same sign. So we hope to have a universally custom designed headgear in the future so it doesn't interfere with any of the facial expressions and movements of the signs. So that is our hope for the future. And so we designed the system for the model's face to connect to the performer dynamics. And it was important for us to have a deaf person develop this and be involved and have a deaf perspective. Andrew just previously showed the system. And research, which is cited, has shown that deaf signers process facial expressions differently from hearing non-signers. And therefore, it is a marker within the ASL language, facial expressions, which is, very different than someone who would not be signing. It's a whole different process, and it's unique to deaf individuals and our language. And so all of those include the eyebrow movements, mouth movements, and eye blinks. So we followed a specific process in production, which included the pre-production, production, and post-production. And we had a lot of planning to make sure that everything was clear and accurate and authentic, so our audience could understand. And I want to emphasize and make sure that it's clear to everyone that we do have deaf natives develop the 3D signing avatars. And I'll pass it on to Joseph.
Now, as you can see, the emphasis of our team is to have all deaf individuals involved so that we can identify facial expressions and easier identify the important parts of the language. And it's important that if we do have hearing people involved on our team, that they are ASL or sign language users. So we want to make sure that we do appropriate testing first before we move forward in a big way. So we first will have our phase 1 preliminary study with individuals interviews. We plan to do that in the spring of 2021. We'll show them different videos and we'll see how they respond, see if they feel that the signing is clear and how they feel about the facial expressions. Facial expressions, again, are very important for ASL grammar and for understanding. And so we have to make sure that people can understand what the avatar is saying, which includes facial expressions. And we want to have one without a cartoon and with a cartoon to see if there are any changes in that. We will change the faces, the skin color, and see if we can measure reactions from people, see if there are different reactions based on that. Then on phase 2, we'll have we'll use questions from language attitudes study that people standardly use to ask individuals about sign language. Well, really any language, but we're focusing on sign language, of course. So we'll use some questions that have been developed to ask people about their attitudes related to sign language. We want to see why they answer that, why they have these perceptions about sign language. And we will include avatars for the language attitudes study, which I'm very much looking forward to. Now, of course, we broke up the presentation between the 3 of us. You can contact any of us if you have more questions about the presentation, about our work, and you can also put them in the chat or the QA. Our contact information will be provided in the chat also. Thank you.
Thank you for that excellent presentation. We have time for maybe one question, and I see a good one here about what application are you looking to use this in or as an add-on to something? So can you change the avatar, or would this be used for interpreters to make the avatars look more like themselves?
I just want to emphasize there was no interpreters that were involved in this study. It was only deaf individuals. Everyone was deaf. And we used Maya. That was the software program that we used. And Vicon technology. And then Performer, the dynamics. for all of the facial features to make sure that everything matched within the facial expressions. And then Maya was developed for the 3D animation.
Joseph is saying also, we had to think about time and resources. We would like to make more races to match a variety of people, but we have to work on, we have to be satisfied with what we have now, use what we have now and see how successful it is, and then work on improving the process in the future. Okay.
Okay. Well, thank you very much. I think we'll move to the third presentation. So if you do have more questions, you can post them in the Q&A and maybe the presenters can answer them in text. But also at the end of this session, we can move to the hubs rooms and you can continue a conversation over there. So with that, let's move to the third presentation, which will be given by Ziming Li, who is a second-year graduate student in the Human-Computer Technology Interaction Program at RIT. So Ziming, would you like to share your screen?
Yeah.
Maybe Joseph need, okay, good.
So hi, good afternoon, everyone. Today I'm going to introduce the RotateEntry, which is a controller rolling style text entry method for 3 degrees of freedom virtual reality device. So many recent commercial VR devices, such as the Oculus Go, Google Daydream, have featured with 3 degrees of freedom controllers. So such a 3 degrees of freedom VR device can support activities with less movement, such as the web browsing, watching videos, and VR socialization. Among this scenario, the text input technique plays an important role. So the ray casting keyboard is a popular built-in text entry solution for this device. While using this text input technology, the user can aim the virtual ray at a particular key on the virtual keyboard and enter the focus character by pressing a button on the VR controller. However, while using this raycasting input, the user has to keep raising his or her arm in use and frequently move the arm in space to aim at a key. So after long-term use, this using posture can cause arm muscle fatigue, maybe resulting in reducing the text input performance and user experience. Also, this interaction would be challenging for those users who cannot keep their arms in the mid-air for a long time. So we proposed the RotateEntry, a controller rolling style text entry method for 3 degrees of freedom VR device. The RotateEntry, it moves a key selecting cursor through the virtual keyboard using the controller's rolling angle and pitching angle. So in this way, the user can put his or her hand holding the controller in any spatial position while entering the task. So based on this RotateEntry concept, we developed 3 interaction methods that look at how to move the cursor across the virtual keyboard. Then we evaluated these 3 interaction methods and the standard raycasting one in a comparative empirical study. However, due to the COVID-19 pandemic, we have to transform this evaluation, previously designed as a face-to-face format, into an online format. So as for the prior study, the ring test proposed by Xu's team and the pizza text from Yu's team have inspired us on designing the text entry interaction for a head-mounted display using a customized layout keyboard. Also, a prior study has also evaluated 4 text entry techniques built for dual controllers VR devices. So these techniques all use a QWERTY layout keyboard with a different keystroke method. However, we found that there's still a lack of study on the controller-based VR text entry method which are less reliant on the using posture or entering text using the controller's rolling input. So the implementation of RotateEntry was to capture the controller's pitching input and the rolling input. The movement of the cursor on the virtual keyboard was to detect based on the offset between the controller's current effective rotational input and the base rotation angle determined by each interaction method. By dividing the effective rotation interval by the number of rows or the number of columns of the virtual QWERTY keyboard, a specific rotation interval was allocated to each key. The key whose allocated interval included the controller's current effective input will be highlighted at a time. So for the evaluation, 4 different text input methods were developed. The first one was using the standard raycasting style interaction, and the other 3 were developed based on the proposed RotateEntry concept. All of these 4 text entry methods share the same QWERTY keyboard layout to eliminate potential effects. So raycasting is a mainstream VR text entry solution. For keystroke, the user could cast the virtual rate to a particular key on the keyboard. While the rotated key, it uses a cursor for the key selection on the virtual keyboard. The user can roll the VR controller to move the cursor among each column. And they can pitch the controller to move the cursor among the row on the virtual keyboard. The rotate column point uses a 2-step interaction, which is roll and then pitch. Firstly, the user can roll the controller to move the column selecting cursor within the keyboard. After the user selects a column, he or she can pitch the controller to move the cursor within the selected column. The rotate column rotate also uses a 2-step interaction, which is roll and then roll. The user can move a cursor among the column by rolling the controller. After they press the key to select a column, the users can roll the controller again to move the cursor within the column. We have conducted a comparative empirical evaluation to evaluate these 4 text entry methods, and the dependent variables are the text entry rate, text entry accuracy, user workload, system usability, and the user experience. And this table shows the metrics of the dependent variables in our evaluation. So as the main task, the participant was required to enter a phrase in a VR environment using the text entry method determined by the condition. Each condition shows 5 phrases selected from the phrase set used in the prior study. And each participant would be presented with a randomized order of the conditions, and the phrases were also presented in a randomized order for each condition. Therefore, each participant would complete a total of 20 tasks. After the participant completes a condition, We will show them the questionnaires that I mentioned on the previous slide to collect the qualitative data. And after they complete all the tasks, we will conduct a semi-structured interview to collect their feedback on each interaction method. And due to the COVID-19 pandemic, we have to adapt the study to an online format. For the adaptation, we conducted a preliminary study to identify the challenges, such as the remote testing control, participants' actions monitoring, and data collection. To address these issues, we have developed a system for the remote testing. This system used the combination of the Zoom screen sharing and a server that could establish WebSocket connection for the client device. These additional developments help the moderator monitor the study progress efficiently, and the moderator can intervene in case of potential issues. Due to the COVID situation, the size of the participant group was very limited. Since our software was only tested on the Oculus Go device, so the participants were selected through the word of mouth based on their accessibility to an Oculus Go device. So in the end, a group of 5 people was recruited. Among them, 2 were males and 3 were females. Their ages ranged from 21 to 28. One of the participants has used a VR device frequently. 3 of them have really used the VR device about 3 to 5 months once. And one of them has never used a VR device before. For those who had used a VR device, they had only used 3 degrees of freedom ones, such as Oculus Go or the Gear VR. And they mainly use the device for entertainment purpose, for example, the playing games or watching movies. Overall, in this evaluation study, we found that the raycasting has achieved the best performance on the text entry rate, text entry accuracy, and the system usability results, as we can see on the 4th pillar. And as for the user experience, it has surpassed the 3 RotateEntry text input method on all GEQ dimensions, but except for the float. Also, we can see a similar patterns on the user workload result. However, it should be noted that about 80% of the participants had experience with the HMDs and using the standard raycasting method. So in this study, we compare the raycasting only as a baseline. So as for the participants' feedback, we found 80% of them indicated that the raycasting is intuitive. However, we noticed that one of the participants indicate that the raycasting was effortful to use. I had to point at the keyboard and then to the exact key. However, while in terms of the rotate key, this participant indicates that a rotate key needs little effort. I just have to tweak and move up and down. It may provide evidence that the RotateEntry interaction has potential advantage on the accessibility issues aspect. Among the 3 RotateEntry text input methods, rotate key used an outstanding overall performance on the user experience. As you can see, the second pillar in the figure is the scores of the rotate key. We can easily identify these patterns on most of the dimensions on the user experience scale. Also, on the user workload result, the rotate key used an outstanding performance compared to the other two rotate entry interaction methods. What's more, it has the highest text entry rates among the three proposed methods. And however, when it comes to the user's feedback, some participants argue that its cursor control is confusing, and some other participants also find the cursor control is difficult when it comes to the role selecting. Last but not least, we found rotate column points and rotate column rotate have a similar performance. We can see these patterns on the text entry rate figure. The first pillar is the rotate column point, and the third one is the rotate column rotate. Also, we can see these patterns on the user experience figure. And on the user workload. As for the participants' feedback, 40% of them have indicated that the column locking mechanism on these two text input techniques is problematic. Other than that, the comments on their controls are various. Some participants may prefer RCP's control, while some may prefer RCR's ones. As for the limitation, firstly, due to the COVID-19 situation, the evaluation only had 5 participants recruited, although the general difference among the 4 methods has been investigated. We may fail to reflect the statistically significant effects on some of the dimensions because of the small sample group. Secondly, the experiment's duration for each participant was around 90 minutes. So in this case, each participant only had about 5 minutes practice time to get familiar with the evaluated text input method, which may bias the performance and experience results of our proposed text entry techniques, since many of the participants were already used to the raycasting one. Overall, in this work, we propose a new text entry solution for the head-mounted displays that can be used with any poster. And we have identified that the rotate key interaction has the best performance among the 3 proposed methods. Also, we have developed a system to adjust the data collection, participant monitoring, and the conditions controlling issues in a VR remote study. So as for our future work, firstly, we will embed a noise reduction algorithm for the input signal to improve the text entry accuracy and usability. Secondly, we may focus on the effects of the keyboard size and the keyboard position in the future. And we will also investigate a customized keyboard layout that may be more suitable for the rotated entry, since in this evaluation, we used a QWERTY keyboard layout, which is similar to the raycasting one. And finally, a larger sample size group and a long-term experiment session will be implemented for the future study. I think that's all of my presentation. And thank you for listening.
Oh, great. Thank you, Zieming. That's a very interesting presentation. There's a couple of questions in the Q&A. I can read the first one. It says, I'm interested in what is the end use? What are you planning to use this for VR experiences, for animations and movies, or as an avatar in a program?
I think because like for the current text entry method on the VR, we have to like focus on the keyboard and have to aim the virtual ray to enter a character. And so we propose this text entry method so that we can focus more on the virtual content itself while entering task. So, yeah.
But do you have a specific application in mind, or is it just for everything you would use this for VR interface?
Yeah, I think it's general solutions for all the text entry method and text entries environment.
And there's a good follow-up question posted, which is, which one do you like most and why?
Oh, personally, I like the rotate key because I think that one is more intuitive. Yeah.
Okay, cool. I have a question myself, actually. I was thinking about how our phones have autocomplete capabilities and suggestions and things. So can you imagine how you would integrate that with one of these methods, where you would put the suggestions or something?
Yeah, I'm like thinking of integrating that kind of features in the future study, because in this evaluation, we just focus more on the interaction method itself. Because if we like integrate the auto completing features, the users may prefer to use that kind of feature instead of like focus on the keystroke.
So after your user studies are done, maybe then you can.
Yeah, we will like have more study on that.
Okay, one final question. It says, have you also looked at where you start typing and then less letters are available to you as you type? Does that make sense? Not sure I get the question, where you start typing. All right, well, maybe we leave that for the hubs discussions. At this point, we can thank all three of our speakers for very interesting presentations here. This went great, I think. I'm happy to have been able to coordinate the session with you all. We are about to move from this Zoom into a virtual world called Hubs. The links have been posted in the chat, so if you're not looking at the chat window, click on that button and you see 3 links. 3 rooms are available. They were all designed by student designers, and so they're all pretty cool to check out. But I would point out that our interpreter will join us in room 1. So if you need interpreting, you should go there. But in all the rooms, there is a text typing capability that will broadcast everyone in the room if you need that. So I see Susan is here. Do you have anything else to say, or shall we close this session?
Just thank you, Michael, and thanks to all the presenters. It was just an amazing session, and look forward to seeing you all in Hubs.
Agreed. Thanks, everyone. See you in Hubs.